Now in this video, inside this single linked list class, we are going to implement a method which deletes a node from single linked list. So as you remember, we have created this class in our previous lectures. So here we have implemented various methods. So we have implemented a method which creates a single linked list, then for insertion, then for traversing of single linked list, then searching for a node in a single linked list. Now here, after searching method, we are going to implement a method which deletes a node from single linked. Now, as we explained in our previous lectures, in the algorithm of deletion of a node from a single linked list, we have mentioned that we have three cases. So I'm going to combine all these cases over here and implement them in a single method. So the first thing that I'm going to do, I'm going to declare our method. So our method will be like this: public void deletion of node. So as a parameter, this method will take only location parameters. So this is the location in which we want to delete a node from the single linked list. Now inside this method, the first thing that I'm going to do, I'm going to check that if this linked list exists or not. So to check that, I'm going to check the head reference. So if head reference equals to null, so in this case, we know that our single linked list does not exist. So this means that we are going to print to the console saying that the single linked list does not exist. So I will print out to the console, the single linked list does not exist. So after doing so, we are going to return, because we don't need to continue to the further, because in this case the linked list is not exist. Then the first condition is we want to delete a node which is the first node in our single linked list. So in this case the location parameter will be 0. So that's why I'm going to put else if condition like this: else if location is equal to 0, then in this case it means that we want to delete a node from the beginning of the single linked list. So we want to delete first node from single linked list. So in case of deleting a first node single linked list, we have also two cases. So the first case is we have more than one element in our single linked list, and the second case is we have only one element in this single linked list. So I'm going to implement both cases over here. So the first case that we are going to implement is we are deleting a node in which we have more than one element in our single linked list. So if we have more than one element in our single linked list, to delete first node, we have to set head reference to the second node. So if I set head reference to the second node, so how can I access the second node? So we know that head reference points to the first node, but head reference's next reference points to the second node. So if I set head reference to the head reference next reference, then in this case, it means that we are setting head reference to the second node. So by doing so, we are setting head reference to the second node, so we don't have any reference to the first node. So in this case, first node will be deleted from the memory. Then after doing so, we have to decrease the size, because in this case, we are deleting a node from a single linked list. So this means that size has to be reduced by 1. So I'm going to reduce the size by 1. So this is the size that we created over here. This is the property of single linked list class. So we have to decrease it by 1 when we are deleting a node from a single linked list. Now this is the case in which we have more than one element. So how can we implement the case in which we have only one element? So I'm going to just do it by writing simple if condition over here. So after deletion of this first node from here, if the size is equal to 0, it means that we had only one element in our single linked list. So if we had only one element in our single linked list, tail and head reference has to point to null to delete this node from here. So in this case, head is already referenced to the null, because in this case we will have only one element. So here we have to set tail to null as well. So I'm going to write if condition like this: if size equals 0 after deletion, then it means that we have to set tail to null as well. So with these 4 lines of code, we have implemented both cases. So in the first case, we are deleting a node from the beginning of single linked list in which we have more than one element, and by writing if condition, we are implementing the case in which we have only one element in our single linked list. So if we have only one element, and after deleting one element, tail and head has to reference to null, so that's why I'm setting tail to null over here. Now then, we are going to continue to the next case in which we are deleting a node from the end of the single linked list. So in this case, I'm going to write else if condition like this: else if location, this is the parameter that comes from here, is greater or equal to size, it means that we want to delete a node from the end of single linked list. So in this case, what we are going to do, we have to find a node which is located before last node, because in this case, if we find this node, then we are going to set the next reference of this node to null, and we are going to change tail to reference this node over here. Now here also we have two cases. So the first case is in which we have more than one element in our single linked list, and the second case is in which we have only one element. So the first thing that we have to do, we have to find the node which is located before the last node. So what I'm going to do, I will start from the head and loop through the single linked list until we find the node which is located before the last node. So to do so, I'm going to create a temporary node over here, temp node, which will be the type of node, which is the node class over here, and it will be set to head because we are going to start from head. Then we are going to loop through these elements until we find the node which is located before the last node. So I'm going to write for loop like this. So for I will start from the 0 because index starts from 0, then it will continue until we reach the size -1. Here we are putting size -1 because we need to find a node which is located before the last node. So in each iteration is going to be increased by 1. So in each iteration we are going to set temp node's next reference, because in each step we are going to next node over here. So this will continue until we reach the node which is located before the last node. So when we reach that node, we are going to implement our cases. So as we said before, to delete a node from the end of the single linked list, we have two conditions. So in the first condition, we have only one element in our single linked list. So how can we check that? So if in this case, temp node reference to head, it means that we have only one element in our single linked list. So if I write our if condition like this, if temp node equals to head, because in this case we have only one element in our single linked list. So when we have one element in our single linked list, we are going to set tail and head references to null. So I'm going to put it like this. Tail is set to head and this set to null. Both of them are set to null. Then size has to be decreased by 1. Then after doing so, I'm going to put return because we don't need to continue from this case over here. Now, if we have more than one element in our single linked list, then in this case, the next reference of this current node has to reference to null, because in this case, after deleting the last node, the node that is located before the last node is going to be last node. So that's why the next reference of this node has to be null. So I'm going to set it to null. Then after doing so, we are going to set tail to reference this node over here, because this is the last node now. So tail has to reference to the current node, which is temp node. Then after doing so, we have to decrease size by one more time. So with this, we are decreasing size by one more time. So with this, we have implemented a case in which we are deleting a node from the end of single linked list. So here we have implemented the case in which we have only one element in our single linked list. Then here we have implemented case in which we have more than one element in our single linked list. Now the last case is in which we are deleting a node from a given location. So here I'm going to put else condition like this. So here we are going to implement a case in which we are deleting a node from a given location. So how can we do that? So the thing is, we need to find the node which is located before this node, then change the reference of this node to the next node which is located after the node that we want to delete. So this is going to be the same logic that we implemented over here, but here we were looking for the node which is located before the last node, but here we are going to find the node which is located before the location that is given from the parameter over here. So which means that we are going to loop through the single linked list until location -1. So to do so, here again I'm going to create type of node class which will be a temp node. So this one also will be set to head because we are starting from the head, and we are going to loop through the single linked list. So I'm going to write for loop condition like this. So int I will start from 0. In this case, it will continue until we find location -1, because we are going to delete the node from the location. So we need to loop through the single linked list until we reach the node that is located before the node that we are going to delete. So in this case, in each step, it will be increased by 1. So here I'm going to set temp node equals temp node dot next, because in each step we are going to do next node over here. So after doing so, finding the node which is located before the node that we want to delete. So in this case, temp node's next reference points to the node that we want to delete. So we are going to change the next reference to the node that is located after the node which we want to delete. So in this case, if I write something like this, node text next dot next, this is referencing the node that is located after the node that we want to delete. So then after doing so, I'm going to decrease size one more time. So with this assignment over here, we are setting current node's next reference to the node which is located after the next node. So with this, the link between current node and next node is broken, so this means that it will be deleted from the memory. Then we are decreasing the size of this single linked list over here. Now with this, we have completed our method. Now let's see how this is working in practice. So here in our main class, we have created a single linked list in which the first element is 5. Then we have inserted 4 more elements over here. Then we are traversing through the single linked list to show the elements of the single linked list. Then we are going to delete an element which is located at the index of 3. So then one more time, I'm going to print out single linked list to the console to see the difference over here. Now, if I run our code, now you see that first our single linked list was like this. Then while deleting a node which is located at the index of 3, 7 gets deleted from here because 9 was located at the index of 0, then 5 was located at the index of 1, then 6 at the index of 2, and then 7 was at the index of 3. So that's why after deletion, our single linked list looked like this. So if I put, instead of 3 over here, 0, it's going to delete the first element. So let's run our code one more time. Now this time you see that 9 gets deleted from the single linked list. So this means that by putting 0, we can delete an element from the beginning of single linked list. So I'm going to try it one more time. So here you see that we have 5 elements. So if I put at index of 6, for example, over here, you'll see that last element will be deleted from the single linked list. Now you see that 8 gets deleted from the single linked list because this was the last element. Because here we have put a condition in which it says that if the location is greater than the size, then we are going to delete an element from the end of single linked list. So with this example, you see that our method works the way that we explained in our previous lecture. So we have implemented all 3 cases over here. So now let's see what's the time and space complexity for this method that we created over here. So for simplicity, I'm going to make it smaller. So here again, we are going to start from the first line of code. So in the first line of code, we have a if condition like this, so in which we are checking that if head equals to null, then we are printing out to the console that single linked list does not exist. So we know that this if condition over here will take a one-time complexity because here we are not performing any operation which is time consuming. Then we are continuing to the next else condition. So in this condition, we are checking location parameter if it is equal to 0. Then we are setting head reference to the head next and we are decreasing this size. And this line of code will take a one-time complexity because these are simple assignment statements. Then we are continuing to this if condition over here. So in this if condition, we are checking that if size is equal to 0, then we are setting tail to null. So this part of code also will take a one-time complexity. Then we are continuing to do this part of code. So in this part of code, we are checking that if location is greater than size. So this if condition will take a one-time complexity. Then we are continuing to the next line of code. So in the next line of code, we have created a temporal node and set head reference to this node over here. And this will take also a one time. Then we will continue to the next line of code. So in the next line of code, we have a loop in which we are looping through the single linked list until we reach the last node. So this means that we have to loop through all elements of single linked list until we reach the last element. So if the number of elements in our single linked list is n, then it means that this loop over here will take or n time complexity. So inside this loop, we have set temp node to temp next. So this means that inside this loop, this part of code will take o one time complexity, but whole this loop over here will take o n time complexity. Then after doing so, we have if condition like this in which we are setting head and tails to null and size decreased by 1. So this part of code also will take o one time complexity. Then we are continuing over here in which we are setting temp node's next reference to null and tail to temp node, and size also decreased by 1. So these are simple assignment statements. So this 3 line of code will take also a one-time complexity. Now at the end, in the else condition, we have created a temp node like this and to set head value to it. And this part of code will take a one-time complexity. Now then we are looping through the single linked list one more time and setting temp node to the temp next over here. So in the worst case, if we want to delete the element which is located almost at the end of single linked list, in this case it will take o n time complexity. So this part of code also will take o n time complexity. Then at the end we are setting temp node's next reference to the temp node next dot next. This will take o one time complexity and size is decreased by 1, and this will also take o one time complexity. Now if we combine all these complexities over here, we will get O(n) time complexity, because in this case O1 time complexities are non-dominant terms, so these ones will be eliminated from here, so the time complexity for deleting an element from a single linked list become O(n) time complexity. Now the space complexity is O1 because in this case an extra memory is not required to delete a node from single linked list. We are just deleting a single node from a memory, so that's why space complexity will be O1. Now with this we have come to the end of this lecture. So in this lecture I have implemented 3 cases of deletion of a node from a single linked list in one method. So hopefully everything is clear about this method. See you in the next lecture.